Hello, this is Mr. Huff, and I want to do an AP Physics review for the semester exam. So this is a follow-up from the review we did in class on Monday. I was going to hit some of the highlights and some of the trickier things we talked about, and also introduce a couple of other concepts that we probably won't have time for in class. So the first one is on the exam study guide, you have a couple of problems like this where you have a modified Atwood machine where mass 1 is right here and it is resting on a frictionless surface. These problems can get a little more dicey if they add friction in, so you have to account for that force that is opposing the tension, but in the problems on the study guide there's no friction, and that's nice. And then mass 2, you have to consider mass 2 down here. When you look at this entire system, the mass 2 is the only thing that's causing an acceleration. So the force of gravity is pulling it down, so we can represent that here. And that is causing this entire system to accelerate. So it's not going to be accelerated at 9.8 meters per second squared because this mass has inertia that is opposing the mass 2 pulling down. Let's look at the formula. So when you look at the force, how it breaks down is you look at the force of gravity right here. That is in opposition to the acceleration of both masses together. So we can break this down a little bit. To get it down to the formula, when we resolve the forces, it's mass 2 times gravity is equal to the acceleration of the sum of both of those masses. So this is just an extension of F equals ma and finding net forces. But if you can get to this point, then you've got it. There's a question, number 13, that talks about applying a force in the x direction and then applying an equal force in the y direction, and you're going to end up with a vector that is 45 degrees from the original position, and it'll be going on in that direction because the surface is frictionless. So think about, you put a force on it going in the x, and then later another force going in y. You have to resolve those two vectors, and you end up with a 45-degree angle. So that's the only choice there. On number 14, it's a little bit of math. As you read through the problem, it gives you this weird term BV, so you just handle that as though it were a force. And it talks about how you have a force of gravity. So I'm going to draw this little free body diagram I didn't include. You have a body, and it has a force of gravity on it. And it's opposed by this other force called BV. So they're in opposition to one another. So we are going to have the force of gravity minus BV will be the net force acting on the object. So that means the mass is going to be accelerated at something slower than gravity. So we have the force of gravity minus BV. And then we move, we want to move A to the other side, or M. This is an M. Move M to the other side so that we can get A by itself and solve for acceleration. So we end up with this term here, mg minus bv over m. And if we separate these two, make it two fractions, where we have mg over m minus bv over m, we can cancel out the m's here, but not here. So we end up with this expression here to solve for a, g minus bv over m. And I don't like how it was written in the worksheet that you had. So that's why when we did this in class, I wrote these answers like this. We talked about in class a cat sitting on a record player, and I also learned that it's kind of difficult to draw a cat sometimes. That doesn't look like something inappropriate, but I guess you had to be there. But if you think about this, the force is acting right here between the cat and the record player. So if you say the force of the record player on the cat, it is a frictional force that is going to be pointing to the center. So this is a centripetal force, but like we saw in the video, the guy said never call it centripetal force, give it a real name. And in this case, it's a force of friction that's making the cat go in the circle. If that friction wasn't there, he would go off in the direction of the tangential velocity and go this way. Also, there is a force acting on the record by the cat. So the force of the cat acting on the record is he's trying to slide off. So he's putting a force on the record that goes out to the right, and this is that imaginary force, the centrifugal force. The only reason it's there is because we have a change in direction because of the rotational motion. So main thing I want you to see is the frictional force points to the center. All right, that should get you through that question. All right, there's this question on the test, and it has something that looks kind of like this. This is a position versus time graph. And one of the things I would recommend is going through and identifying where your velocities are and what they are. So let me find a nice color here. So here we have the first segment here. We have a big negative velocity. And then right here, it is a small negative velocity. And if you go from, I'm just going to draw a little number line down here. So we have 0. If we have a big negative velocity and we're going to a smaller negative velocity, the acceleration there at this point is positive. Okay, because it's slowing down. So the acceleration is to the right on the number line. Okay, so let me erase that. When we go from this small negative velocity to a large positive velocity, we have a positive acceleration. It's still going to the right on our number line. At this point, it goes to 0. So when we go from a big positive acceleration to 0, this acceleration is negative. When we go from 0 to a positive velocity, we have a positive acceleration. And right here we go from a positive velocity to 0. So this is a negative acceleration. And right here we go from 0 to a big negative velocity. So this is a negative acceleration as well. So that's the kind of thing you need to be thinking about here. What's happening? What kind of accelerations are you seeing here? Think about it in terms of a number line. And if it's moving to the right, if it's going to the right on the number line, it's positive. If it goes to the left on the number line, it's a negative acceleration. So keep in mind that this is a position versus time graph. So the slope tells you something about velocity. When you see a change in slope, that's telling you something about the acceleration. I want you to think about two things on this one. The force of gravity is equal to the universal gravity constant, big G, times the mass of the larger object times the mass of the smaller object divided by the radius square. Remember that radius is the distance between the centers of two objects. So that would be the distance. Let's see. I wanted to talk about gravity. If you wanted to determine gravity of a planet, you would need to know the mass and the radius at a minimum. Okay, so you need to know mass and radius, and you need to also think about what would happen if you double or triple. Let's say if you just manipulate these variables. What if we took mass, the smaller mass, and made it times 4, and we took the radius and we made it 3 times? So you would you need to think about how to determine what your force of gravity would do if you manipulate those variables like that. So let's think it through a little bit. So you'd end up with 4 times the mass on top, and then down here at the bottom you're going to have 3r squared. And if you square that, so you end up with 4 over 9 times, your gravity is 4/9 of the original, if you think about that. So if you're not clear on that, let's do a couple of these in class or in TESOL. Okay, so think about manipulating the masses. Really, I would prefer to think about that as comparisons. All right, you need to, on your own, think about, make up some numbers and see what happens. I want you to compare the frictional forces acting here and acting here. If you're pulling this one up a slope with a given angle and the same mass across a horizontal surface, so make up an arbitrary value for mu, like 0.2, and make up a mass and compare and make up an angle and compare the force of friction between these two. And that will guide you to an answer. I think if you actually do some math there, you will that answer will be clear. You need to think about this this kind of scenario where you have tensions between two masses, or two masses being pulled on two different ropes. So think about the tension between these two and compare it to this. And then if you can identify that, you could also do a free body diagram here showing that this only has a tension here for the big mass. The small mass will have a tension going this way and a tension going this way. So think about that. And then if you thought about the whole system, then you just have, it'll look more like the first drawing. There's going to be a problem, or is this on? Yeah, this is on one of the problems on the study guide. You need to think that, remember that the definition of power is the rate of work. So power is the rate of work. And you can also think about the work being a force times the distance. And you can also think about velocity being distance divided by time. And in this situation, if we're pulling this block with a force going at a constant velocity, that means that the force applied and the force of friction are equal and opposite. So we can start substituting some of these values. We can replace work with force times distance, and if the force of friction is equal to the force applied, we can replace the force with mu times the normal force of that mass. And if we wanted to break that down even further, we know that the normal force is mass times gravity as long as it's on a horizontal surface. So mu would be, or not mu, the force of friction is mu times mass times gravity. And if we're talking about a constant velocity, it's distance divided by time. So you can think about how to put these three formulas together to end up with this more sophisticated expression for power if you know the mass and the coefficient of friction and the distance and the time if the velocity is constant. So that's a little bit of algebra there. We've talked about what happens if this is mass 1 right here. Oh, that was a terrible thing to do. We have mass 1 right here, and we normally say this is a massless, frictionless rope, okay? But what if the ropes were not massless? So on this side, we have a couple of ropes holding this up, and they have mass. So what's going to happen in this situation is as you look at the tension in these ropes, starting from the bottom going to the top, the tension down here is equal to mass 1. But the tension at the top is going to be equal to mass 1 plus the mass of these ropes. You have to put all of those together. It's going to be the sum of both of these at the top. And if you go halfway in between, it's some value in between the mass 1 and mass plus the mass of the ropes at the top. So it's going to vary from 0 all the way to the highest value of mass added to mass 1. I hope that makes sense. All right. That's all I have for now.